Thank you. If you have any questions, that was my talk. I know it's the last talk, so I'll try of the day, and it was long, and I'll try to keep it as light as I can. So yes, I want to talk about a line of research that has been kind of booming in the last 6 years, starting from an idea that comes in algorithmic fairness, and this multi-group fairness notion that I'll explain, and that kind of grew to directions that we didn't expect. And by now, so usually at the beginning I would write all of my collaborators in this area, but it became very big, and it also grew way beyond. So every now and again I find more people that work on it, and I hope that perhaps I'll enlist any of you. So, well, why? What's the, yeah? Okay. Unfortunately, I'm going I'm teaching tomorrow morning, but I'm leaving behind me Vatsal, and you can talk with him throughout the workshop. He was already enlisted, sorry. Okay, so algorithmic fairness comes from what we all know that, it started before, but the boom in this research area is through this idea that algorithms are making and informing decisions in a variety of areas. And just like we expect humans that make decisions to be fair, we also need algorithms when they make decisions to be fair, whatever it means, based on whatever laws, ethics, regulation that exist. Okay. With that growth, it's not only fairness. I mean, there's a variety of questions at the center of discussion in society that are all about computation, or much of it is about computation. We heard a couple of talks about privacy. Privacy perhaps is the most advanced topic in this line of research. There are questions that are very much behind. And today we're going to talk about fairness, and this is the concern that algorithm will discriminate against groups or individuals that are protected by law, policy, or ethics. And this, perhaps when we started talking about it, we had to kind of invent kind of potential risky scenarios in 2010. But since then, it's obvious that this is a real issue, and various companies have had eggs on their faces, and the sentiment within the public also changed from this idea that computer scientists are these geniuses saving the world to the idea that we are the evil geniuses that are about to destruct the world. So if we all care about being geniuses, it doesn't matter, but the direction matters. So CS theory was there from the start, at least in this notion of algorithmic fairness, at least as far as this kind of machine learning driven revival of this area. There is algorithmic fairness beyond machine learning, before machine learning, but I won't discuss any of that. And in that, we are trying to follow examples that come up in cryptography, game theory, and other areas where the right definitions, right abstractions have made a big difference. And since then, there's a lot of scientific and practical impact, and I'll talk a little bit about it. But there's also a growing sophistication and connection to many sub-areas, definitely many other areas. It's an interdisciplinary area, so beyond CS, but also a lot of sub-areas within computer science, within theory. And computer science. So whatever your interest, we can find the right question for you to care about. Oops. So let me start with kind of this notion of multi-group fairness. I'll try to focus on the learning part. So So yeah, my title was long, but also the title of this workshop. I'm not completely sure I understand it, but I think you'll find in this at least computational and some gaps and some learning. I don't know about statistical, so I think that I have at least 3 out of 4. So the computation kind of motivation to a very computational approach to fairness that translates to a new kind of computational perspective on learning. Of course, learning is computational at its essence, but we'll see what I mean. So the prevailing approach to learning, to fairness in learning, and still the one that you'll find in most papers that talk about fairness, whether they say that we have a fair algorithm or they say fairness is all nonsense, it's because they interpret fairness as these group notions of fairness, meaning that, so all of these definitions have the following form. You look at one protected set, S, perhaps defined by a protected attribute, gender, race, ethnicity, etc. And you want this protected set to see the same behavior as the general population, the same behavior based on some statistical parameter. Also, we do have some statistical. Okay, good. We're completely covered. So notions like statistical parity, calibration, balance, other notions are all of this sort. And this is really the approach you'll find in most discussions on fairness. It's easy to understand. It's easy to understand, easy to get, but very, very weak. It's very easy to abuse. It's a game we've been playing since 2010. Find ways of abusing these kind of group notions definitions. Very amusing game, apart from the fact that it corresponds to real life discrimination. And they are at odds with each other. There's one of the things that caused another round of excitement from this area is impossibility results that show that you cannot get very natural notions simultaneously. And there's always the question of which group we want to protect. It's a very deep question. I won't discuss it here, but happy to discuss it offline. So for me, in my research, a major challenge was to understand the extent in which we can retire, or at least weaken the impact of group fairness notions.
Sorry, what do you mean by retire here?
Retire is that when we talk about fairness, we will not talk about these notions, or not only about these notions, but we'll talk about more sophisticated notions. So perhaps that's an extreme.
So it's not relevant, or it's already easy to achieve?
I mean, it depends on, it's like with lower bounds, right? Or if you show that something is impossible, something very weak is impossible, then it's useful. And it's useful to expose trade-offs already. So I'm not saying that it's useful sometimes as the first question you ask, but it couldn't be the entire thing we think about when we think about fairness, the thing that we are trying to obtain in real life, for example, or our definitions that we are kind of trying to enforce by regulations. We want things that are a bit more subtle, a bit more powerful. So with this in mind, we introduced many years ago this notion of individual fairness that I will not discuss here. And what I'm going to discuss is this notion of multi-group fairness. And I'll tell you a little bit about why is it natural from algorithmic fairness perspective. But for it to be useful, it's not enough for us to present something and say, okay, that's a useful thing. It will never be applicable if it's only from the point of view of fairness. We need to create an entire understanding around it, a much more deep understanding, especially about the learning aspects of it. And this literature has been growing a lot, and I'll tell you a little bit about that. And interestingly, some of it seemed to have usages beyond the fairness aspect. You can, by the way, interrupt me. I can drop some of the stuff at the end. So let me give 2 examples of why this is kind of insufficient, these notions of group fairness. So the first one, I didn't change it after our lunch, but it's advertising a burger joint. And we have some protected group, S, that we want to protect. And we're going to consider the case where you want to advertise this burger joint, but you are S-ist. So you're against people from S, you want to exclude them from your burger joint. And, but on the other hand, you are required by some regulation to satisfy a very restrictive notion, which is statistical parity, which says that you need to advertise with the same probability to people in S and people outside of S. Sounds very, very strong. At times it's too restrictive. But our evil genius decides to advertise to vegetarians in S and carnivores outside of S. So you satisfy this requirement while excluding people from S. So protecting group requires protecting relevant subgroups, but these are not subgroups that you can easily identify ahead of time. These are subgroups that sometimes are as strange as carnivores in S or West Coast carnivores in S. So these are, the groups will change from one application to the other. Let me move to a different thing that will be relevant to one of the topics that I want to introduce is the meaning of individual risk scores. So much of what we're producing through machine learning, is various kind of predictions on the probabilities that some event will happen to an individual. The probability that they will repay a loan, the probability that they will suffer from some medical condition, the probability that they will successfully complete their studies. But what is the meaning of individual probabilities or individual risk scores when these are events that cannot be repeated? I personally will have this medical event or not. Where's the probability here? Of course, we didn't invent it. It's a very big debate within statistics for many generations. I should have recommended a wonderful survey by David. And if you thought that there are only 2 approaches for it in statistics, there are many more subtleties there. And what we want to do is introduce a computational perspective that kind of interacts with these notions, but perhaps has a different aspect to it. So as an example, let's imagine that you go to your physician, and the physician tells you you have a 4% probability of some medical condition, 4% of having a heart attack in the next 10 years. So based on that, some medical decision is going to be taken. And you ask, okay, what does it mean? So the physician tells you, there was this study, and in this study that corresponds to people like you, 4% of them had a heart attack in the following 10 years. So you go home and you search the web and you find a different study when there is 10%. And it's a study that also captures you because you're part of many groups. So then what does it mean to you? Perhaps it means that it's 10% or 4%. And in fact, what happens if the other study also gives 4%, but it's a different group? So does it mean that it confirms that you have 4% probability of having a heart attack? Or perhaps you have a higher because now you're part of 2 risk factors. And in fact, what happens if you found a different study, it doesn't capture you, but it captures some other people within your group. So perhaps you're having a much lower probability because these are the people that having high probability. So the question is which group? And that's a question that has to do with fairness. Each one of us has a multitude of identities, and deciding to view us as a member of one particular group is a major decision. It's not clear which group to view as. And there are examples in which this can be leading to discrimination. So the idea is that we have a multitude of affiliation, and multi-group fairness tries to respect a large number of these affiliations. So I want the physician to give me predictions that make sense when I'm viewed as part of this group, but also when I'm viewed as part of many other groups. That's kind of the motivation. And I'll say that this gives us this computational perspective of individual risk scores, and we'll see it soon through this notion of outcome indistinguishability. Good. So which groups? As we saw, there's the meaningful of protections to a group depends on protecting relevant subgroups. And we don't know a priori which subgroups they are. Perhaps they are qualified loan applicants. Perhaps there are carnivores in S. These are groups that it's hard to predict ahead of time. So what this line of research said, we want to offer fairness protection to every large enough group that can be identified given the data and given computational limitations. So for example, any group where membership in this group can be identified by a depth 5 decision tree, or perhaps by, and actually this sounds extreme, but by a neural network, and there are results of this form. So for each one of these groups, many more than you would usually protect, you want some protection. Specifically, the notion that we'll be focusing here is on multicalibration. And so then protection, quote unquote, because by itself it's very weak protection, means that for every set in this collection of things that we can deal with, things that are defined by these small neural networks, for each set I want calibration. What calibration means? It means that the predictions are calibrated, meaning that they mean what they say. So if I look at all the individuals for which I predict 1/3 for some event, roughly 1/3 of them are going to see this event. As we said, we don't know what individual risk scores are, but over sets we can definitely estimate probabilities. For a random individual in T, for which we said 1/3 is the probability of a positive outcome, 1/3 is what's, roughly 1/3 is indeed the probability of the outcome. So that's our notion. And as I said, there's a lot of research in the last 6 years. Since I won't cover a lot, I wanted to direct you to this workshop that existed a year ago, Multi-Group Fairness and the Validity of Statistical Judgment in the Simon Institute. So if you're missing things to watch, a lot of good talks. I'll just say that it's a year old, and some of it is already been updated, and there are newer stuff to show. I also say, and I won't talk much about it, that very scarily for a theoretician like me, some of these things already found their way into practical applications. But we'll ignore that from now on, because it's a mathematical institute here. Okay. Yes?
Is there any simple rule that if it's fair with respect to, let's say, T and T prime, then it's also the same with T intersected with T prime or union?
No, and that's some of the problems. So when we say which groups, I didn't get into this notion, but one of the things that we care about a lot is intersectionality. And some of the examples that I flashed for discrimination are exactly of this form, that you can have a situation where on average you treat one group well, and on average you treat another group well, and the intersection is treated badly. Or perhaps more common, there is a set that you treat badly, and another set you treat badly, and the intersection is treated worse. So this kind of more cumulative aspect of it. So the gender shade is one such example. So you need to be specific about the groups you want to deal with. Good. So let me kind of try to, again, a very high level, try to kind of share what is kind of the philosophy of this paradigm. The philosophy is that if usually we learn to optimize, so we have some loss function, for example, in mind, or something we want to optimize, and we find the point within this space, the hypothesis that minimizes the loss, maximizes utility. The new approach is to first learn, and learn in kind of indistinguishability sense, and pseudo-randomness sense, meaning we want to learn something that looks like it's the real thing, like it's the base optimal predictor for many tests, for a large collection of tests. And what this will allow us in many senses to optimize later for various downstream applications. So this is kind of the high-level theme that we're going to see in several incarnations. Indistinguishability, of course, within learning, the connection within indistinguishability and learning is not new. Definitely it was highlighted, for example, by the work on GANs. But I think it's a different kind of indistinguishability. So it's a different example of this theme. Okay. And so what do we learn from it? We learn various things about learning that we'll talk about. But I also want to say that this kind of approach also tells us something about fairness. So one thing that I think we can demonstrate and there are various works that demonstrate it, that there's always a question of whether fairness is about, whether accuracy can ever be a notion of fairness. And what we learned kind of is that it's a useful, even if our goal at the end when we're choosing actions is something that's not fairness, perhaps some kind of affirmative action, we first want to find the predictors that are as accurate as possible and that their accuracy is distributed well among a lot of subpopulations. And then when we enforce some other notion of fairness, even these group fairness that we talked about, that are usually quite weak, when we enforce them over something that perhaps is multicalibrated or outcome indistinguishable, we get a much stronger guarantee. And many of the weaknesses of these these group notions disappear. So there too, in terms of fairness, it makes sense to first shoot for accuracy, and then when you do whatever, when you decide what to do, you can decide based on a variety of different constraints. Okay. So let's see some of the things. So it's a new kind of paradigm, and there's been lots of different, it doesn't cover everything, lots of different notions. We already talked about multicalibration. And next we're going to talk about outcome indistinguishability. That takes this idea, so already in multicalibration what you have a predictor that satisfies a lot of tests. These tests are calibration tests. But this outcome indistinguishability makes the point even stronger, and you'll find a predictor that is in some sense indistinguishable from the base optimal, from the true thing. Another notion is multi-group loss minimization. So for a large variety of groups, you may want the loss to be small. And this it's not guaranteed by just optimizing loss overall. This loss could be distributed very differently if you don't insist on it. a notion of universal adaptability that we won't talk about that gives a lot of robustness to distribution shifts without knowing ahead of time what shift it is. So you don't need to learn propensity scoring. It's an alternative paradigm. And we'll talk more about omnipredictors, where you don't need to know the loss function you care about ahead of time. Good. So that's the plan. Just say that with the new paradigm, there's lots of new questions. There have been lots of papers, but there's still lots of questions. So again, more people to do. So the natural questions like sample complexity and algorithms and minimal assumptions, minimal computational assumptions, the relationship between all of these objects, and applications, fairness, robustness, prediction-based algorithms. I didn't add it just because of Ravi's talk, but it's a slightly different notion than in his talk. And also other settings, online. So this notion of multicalibration actually can be found in the different incarnation in the forecasting literature, and we're bringing back some new insights to this literature. Real outcomes, performative learning, constraints that can be capacity and fairness, some kind of affirmative action aspect to it, conformal prediction, causality, lots of different settings and lots of good questions. So let's start with outcome indistinguishability. Okay, so very little in terms of notation, being the last talk. Mostly I want us to agree on the notation. Nothing should surprise you here. So we have a distribution on individuals, attributes, and outcomes. And we'll talk about Boolean outcomes. But this could be generalized. Some works do generalize it. And we want to learn a predictor, which is a function from the attributes of an individual, let's say a d-bit vector, to a number between 0 and 1 that we will interpret as probability. Although we don't know exactly what these probabilities are, this is how we're going to interpret it, which should approximate the base optimal, which is p star of x, the probability that y equals 1 condition on x. And again, it's not completely clear what the base optimal means in real life when you only see one individual. So perhaps we should think about it as 0, 0, 1 thing. Perhaps there's no randomness, perhaps there is randomness. The results just are more general when it's not a 0, 1 thing. Okay, so that's the setup. Nothing surprising here. So this is example, okay, many of you of course know pseudo-randomness very well, but I like this example, and it captures something perhaps surprising. So this is an example from Avi Vigdersson, and talks about coin flip. So if there is one notion of randomness that we are secure about and we know what it means is a coin flip, let's say it's a fair coin flip, a fair coin, and when we kind of have this game where we flip the coin and now we need to guess if it's going to be heads or tails, then at this point we can assume, I mean, there's nothing more that we could do than, it will look to us like it's a random coin flip. So this kind of capture a random event that is happening with probability half, a random coin. But even this simple thing can change if the same coin flip, now we have lots of sensors that are monitoring this, that are connected to a computational device, then it could be that immediately at this point we can say with probability 1 if it's going to be heads or tails. So here, P star in this story, which is essentially the same story, is either 0 or 1. Which means that randomness, right, in the eye of the beholder. But what does it mean? It means that it relates on the information we have and also on our computational power. The sensors by themselves would not do a lot if we don't have a computational device to match them, and the computational device would do nothing without the information. And that's something that will be mimicked in our predictors. So computational indistinguishability, very briefly is kind of one way of capturing it is through this idea of blind tasting. And so you get a glass, which is either the more expensive wine or the decoy, and you need to guess whether it's that one or that one with probability better than half. I did it twice in my life and failed miserably. But in that case, when you can't distinguish between that, then to some extent, this cheap wine is as good. So you're kind of saving resources, which is essentially what pseudorandomness does. It saves resources and gives you something that's as good, which then correspond to a definition of pseudorandomness. You can have a blind taste where you get a sample from one of the distributions, and you need to decide which it is. And if you cannot tell with probability much better than half, then this distribution is pseudo-random. And therefore, perhaps it saves bits or something, and it's as good. Like the cheap one, it's as good. So that's all good, but what's the role of computation in our prediction? So how does it factor in? So again, we have this Bayes optimal that we want to approximate from these examples. And individual accuracy is impossible unless we assume something very strong about nature, that this distribution is somehow simple, then there is no chance of telling the probabilities of individuals that we didn't see. But in fact, any level of accuracy relies on computational resources. Because if in reality P star is indeed for half of the people 0, for half of the people 1, and the distribution on zeros and distributions of ones are computationally indistinguishable, then this world on the left with P star is in some sense indistinguishable from the world where P tilde is half for every individual. So if now we switch the world and it now operates based on this rule, we cannot tell the difference. So in this sense, P tilde is an outcome indistinguishable version of P star. So cannot distinguish nature from this hypothesized nature based on empiric data. So kind of a little bit more about the definition. We have lots of variants and relations, but I'll skip all of that. A predictor P tilde gives a generative model of outcomes where for every x, the outcome y is sampled based on P tilde of x. And let's y tilde of x be the simulated nature. So not the real outcome, but the outcome that is generated based on this predictor. Outcome indistinguishability in one version, the version perhaps one version, says that the following two distributions are indistinguishable. The individual in both of them, the prediction in both of them, and then the simulated outcome and the real outcome. These two are indistinguishable. And this is, of course, a definition that depends on the data, for example, on the x's, how rich they are, how rich are the attributes to get, and on the computational resources. But this means, in some sense, that if now, instead of seeing the real nature, we see something that works based on our model, then we cannot tell it apart. Which means, to some extent, this is kind of an interpretation of individual risks scores. It means that these scores are, to some extent, indistinguishable from nature. They give us a model of nature that is not refutable. So a little bit about the interpretation and the construction. We may be completely unhappy with our predictor P tilde. For example, we perhaps don't believe in randomness. We believe that every person has kind of a real kind of number on their forehead, 0 or 1, and this determines what outcome there will be. Quantum doesn't factor into these things. Either they'll repay the loan or not. succeed in school or not. There's just a lot of information, we don't know it, but these are real numbers. These are integer numbers, zeros or ones. So if p tilde doesn't do that, like it's half, then we know that this is not nature. We don't believe that it's nature. But we can still not refute it just based on what we see. So this is kind of a version of individual risk scores, individual probabilities in the eye of the beholder from a computational perspective, which kind of interacts with some of the approaches in statistics, but it's a very computational interpretation. This version that I gave you is equivalent to multicalibration. So since we know how to build multicalibrated predictors, which I won't discuss kind of what's the complexity and all of that, we just as well can construct outcome indistinguishable predictors. So
so the equivalence here, so multi-calibration depends on some specification of a set. So sort of implicit in this is the notion that the sets that you're multi-calibrated with respect to are the things that can be identified by computational.
So you're right. Both of these notions are kind of defined by a family of tests. Multi-calibration are by calibration tests, and outcome indistinguishability by more general tests. And essentially so there is a simple transformation between the distinguisher in one setting and the sets in the other setting. And in fact, if you do the right definitions, they are almost the same. So these are syntactically they are different. So the equivalence is not exactly that, but the transformations are very, very simple. Thanks. So what's the good news? The good news is that we can come up with a very strong guarantee that is obtainable, or in many cases it's obtainable. And which means that we get P star that is as good, P tilde that is as good as P star in particular settings. The bad news is that individual predictions may be way off because outcome indistinguishability is kind of a weakening, and multicalibration is a weakening of L1 distance. If you really wanted individual probabilities to make sense or to be close to truth, you needed L1 distance or something of the form. And this is kind of a computational weakening of it. So you can have something that for individuals is very, very different than real life, but you won't be able to observe it unless you increase your computational power or you gather more attributes. And there's lots to discuss here, which I will not. So I would say that this does give us so there are stronger notions in sample access that have better ability to audit for mistakes. So sometimes you need to be able to, for example, if somebody gives you a software that tells you that this gives you prediction for something important, repaying loans, recidivism, sometimes you can audit for problems better if you have access to the program rather than you just see individual predictions from this program. Lots of insight that I won't discuss. Okay, so if there are any questions about outcome indistinguishability, and if not, we're going to talk about omni-predictors. I'll mention multi-group fairness, but and won't talk about universal.
So I have maybe a high-level question.
Yes.
So, from like a learning standpoint, like calibration sometimes, is a kind of weak goal, and as you talked about, right? Like I think one of the famous examples is the Foster-Vora stuff, where you can get calibrated predictions of the weather without knowing anything about the weather.
Right. So the other way of thinking about
I'm just curious how you think about that aspect of this.
So another way of thinking about it is as a positive, the forecasting literature, positively is saying that you can get, so you want to get, and here too, an outcome indistinguishability, for example. If there is nothing to do, if the world is really zeros and ones that are indistinguishable from each other, then you cannot do better than just saying uniform for everybody. But if there is a rule within your computational ability, then this will be exposed by outcome indistinguishability or multicalibration. To some extent, so one of the original motivation of that was this impossibility between calibration and
equalized odds.
Equalized odds. And equalized odds ask you to do good on things that are not defined when you need to decide, on the outcomes. The positive set and the negative set are not defined when you're making the decision. So instead, this approach of multicalibration says, I want you to do well on every set that is defined at the time you're going to make a decision. And if there is no set that makes sense, then you won't do anything good. But perhaps that's what you can.
I guess what I'm wondering is part of the way that sometimes one achieves calibration is by cutting up the space into smaller pieces and then adjusting the predictions on them.
Yeah.
And to a certain extent, when calibration can be achieved without knowing anything about it, it would almost seem to me that you want, a good mark as a predictor that's both simple and calibrated.
Right, so here the thing is that you get, there is a huge difference between calibration and multi-calibration.
Right.
And it's completely unclear how to, even if you think about calibration for all the sets that are defined by two protected attributes, ethnicity and gender. So you have a division of groups here, a division of group here. How do you deal with all the groups? The one way you can do it is by intersection, and then you do something stupid for the intersection. But if you have lots of intersecting groups, it's completely unclear how to do that. And that's why we can get things like these omni-predictors. Okay. Loss minimization. Okay, I'll be running ahead. Again, that's not the group to explain, and I'm not the person to explain to this or any other group, but I found myself here. But I wanted notation, so you have the distribution as before. You have an hypothesis that it's tied to an action. Should you test a person, what dosage to give of medication? You have a loss function that depends on the outcome and on the action you've took. Like LP distance or LP loss. And you want to minimize the expected loss. Different loss functions may imply different optimal hypotheses. Not hard to come up with examples. And I'll just say in 2 words that this kind of introduces this notion of multi-group loss minimization, where you want loss minimization not over everybody, but for many groups, like we have in multi-calibration. And this can be done through outcome indistinguishability through multi-calibration. This is a work of Rothblum and Yona. Which loss? Many possible losses. Again, I don't want to talk about it too much here. I just want to make the distinction between proper losses, where the action should be just the prediction, the best prediction, and non-proper losses where there is some kind of post-processing. Once you tell me what's the probability of a positive outcome going to be, even if it's a non-proper loss, it's very easy to tell you what's the action you should do. And it doesn't depend on anybody else. It only depends on this probability. And so this post-processing KL is where it depends on the loss. But again, if you know all of these loss functions are easy to optimize, if you know the actual probability, the P star, where the event is going to happen. Different loss functions minimize minimized by different algorithms, and are minimized by different models in your set. So this is Parikshit's kind of image that the different models that you get give you different aspects of reality, like the story about the elephant. So in the paper, we have this example of a very simple example, binary classification with different false negative costs. And you can see that each one of them, for each ratio between false positives, false negative costs, you get a different classifier, and you cannot recover one classifier from another. If, on the other hand, we knew P star, it would be very easy to optimize all of this. We'll do it by taking a different threshold, depending on what's the difference between the loss of the false positives, the loss of the false negatives. So the approach that we would like is to learn somehow P tilde that will be as good as P star for this purpose for a variety of loss functions. Okay. And this cannot be done because different models will optimize for different losses. You can't just give me something out of C. You need to go a little bit beyond the complexity of C, but we can see that you don't need to go much further. Okay, so I'll perhaps skip this additional. I'll just say that there are many reasons for which you want to deal with lots of different loss functions. You have a prediction of the probability of some medical event, and you can make various decisions based on it. Do I give daily aspirin? Do I suggest another test? Do I suggest surgery? For each one of them, there is a different loss function that you need to take into account. Perhaps there are some loss functions that are going to happen in the future. There is a new medical intervention that we didn't think about when we came up with it. So what we can show is that multicalibration implies this notion of omnipredictors compared with the same class C. And the intuition is that P star is good enough to minimize any loss absolutely, and OI kind of imitates P star. So let me skip that to give the more formal definition and notion. And again, you can interrogate Vatsal after my talk. So for a family of loss function and a family of models, an LC omnipredictor is a predictor such that for every loss, I missed the next, I missed the punchline. For every loss, when you take this P tilde as if it was P star, you get something that optimizes the loss compared to everything in C. So yeah, sorry. So if we go here, the loss that you get by any member of the class C will be larger than the loss you get, or up to some error, than the loss you get by taking the predictions and post-processing them like this with the optimal post-processing. Okay, I see that I'm running quickly out of time, so let me skip to the end, I think. Sorry. Let me just say that the theorem that we have, one of the theorems, there are lots of interesting theorems, but if you look at the set of convex loss functions, Lipschitz convex loss functions, bounded loss functions, if P tilde is C multicalibrated, then it is then it simultaneously optimizes for all of these loss functions. So you have one, as Parikshit likes to say, one prediction to rule them all. Okay, so that's one theorem. There's a lot in this literature. I'll just say that in some sense it says that this P tilde is a point on the way to P star for everybody. There is a Pythagorean theorems that related to it. Geometric interpretation, I'll also send you to Vatsal for all of those. Okay, lots of questions, lots of different results. I don't want to hold anybody. So multi-group fairness is a powerful new paradigm from the perspective of algorithmic fairness. It's somehow between group fairness, which is pretty weak, individual fairness that's very strong, but is also harder to obtain. It gives us this perspective on learning through multicalibration or outcome indistinguishability. And this has lots of applications like omniprediction, and omniprediction in a variety of settings. There's already a rich theory, but many more open problems. So these are the gaps that I wanted to mention. And perhaps I'll leave this as a last page. Thank you.